Hi everyone and welcome to a new video about control systems topics, and we're continuing with the subject of from Bode plot to the transfer function of a given system. And in this example, example number 6, I will continue with the example of a Bode diagram having a gain peaking. So in example number 5, we also discuss a situation where there is a gain peaking. So this is our second example of a Bode diagram with a gain peaking. So let's move on. So what we have, again, a situation where we want to determine the transfer function from a Bode diagram, and in this situation we have a gain peaking again, as shown here. There's a gain peaking somewhere. We will determine that very shortly. And there is some gain here, in this case a DC gain. So let's zoom in. We will see the details step by step in the following analysis. So what you see, this is the complete Bode diagram with a phase and also the magnitude. You can see that there is a gain here which starts very constant. So there is a gain, let's say, between 5 and 10. It's a little bit larger than the midpoint, so I estimated at 8 dBs, and it then stays for the first part nearly 8 dBs, and it starts to increase, and then reaches a maximum. There's the gain peaking, and then starts to decrease again with a specific slope. What you see also here is there is actually a situation where the phase is 0 degrees, 0 degrees at 8 dB, so there is no sign inversion in our gain, and the phase will increase, and this phase increase is actually due to 0. So I expect that there is a 0 somewhere here. So we have the gain peaking, but the gain peaking is not caused only by the pair of complex poles. We have discussed it in example number 5, the previous example. So the gain peaking will cause, of course, will be caused, of course, by the pair of complex poles, but there's also a gain peaking due to the 0 alone. So we will also consider that. So let's move on first with this first step by drawing the asymptotic line for our DC gain. So that's our first step. So let's make this red line. This will give us the DC gain for our system. So that is around 8 dB. I will use that later. Now, what we next will do is, of course, I estimated there is a 0 here. So what I want to do is I will draw here shortly at a line that has a slope of plus 20 dB per decade, because the 0 will contribute plus 20 dB per decade, a slope in our Bode diagram. So it will contribute a positive gain. So if I make a first sketch, I will start at, for example, 0 dB, and I end at 20 dB. So there's an increase from 0 to 20, and I will increase the frequency from 1, which is 10 to the power 0, to 10 to the power 1, which is just 10. So I make the frequency 10 times larger, and I will increase the gain from 0 to 20. So this is actually the line. So I will use this line. I will place this line tangent to this part of my graph, such that I can determine the intersection point between this red line and this green line. So this intersection point doesn't mean anything at the moment, so there's just a line here that we can use. And if I now move this line towards this black line, our gain plot, I will have the following. So as you can see, I start now here with the green line at 5 dBs, or again the same frequency, 1 radians per second, and I will end here at 25 dB. So there's again the same slope, so 5 and 25, there's an increase of 20 dB, and my frequency has increased by a factor of 10, so still the same slope, but I have now the green line tangent to my gain plot. Now I have now an intersection point between this red line, which is given asymptotic to our DC gain, and our green line, which is now tangent to this part of our graph. And I see here an intersection point. So this intersection point, let me make this clear with a dot. So there is this intersection point. This intersection point will determine our 0. Of course, it's an estimate, so it can be a little bit to the left side, maybe a little bit the right side. So I estimate that this is between the 1 and the 2 radians per second. This is, of course, not a linear scale, so I cannot say that it's just 1.5, but I don't know what it exactly might be. So it can be, of course, 1.3, maybe 1.7, I don't know, but I will still take 1.5. So it is an estimate. We will try to It is definitely not 1.1, for example, also not 1.9. So it is somewhere in between. So I will take just 1.5. So if I make a drawing vertical from that point to the vertical for the frequency axis, I will get this orange line. So I think this is 1.5 radians per second. The next step is determining actually the peaking and also the frequency where this peaking happens. So let's move on with this analysis. So if I now place the dot and again directly the vertical line to the frequency axis, I will get this section. So this peaking, as you can see here, is around 21, maybe 22 dB from this 8 dB. So I have a total peaking from 8 dB to 22 dB. So it is 14 dB increase. But again, as I said earlier, this total gain peaking is not caused only by this pair of complex poles. It is also caused by, this increase in the gain is also caused by the zero. So if there are no zeros, you will have a lower gain peaking. So how do we then determine the actual gain peaking for determining the expression for the pair of complex poles? That is a very good question. So again, we estimate, we don't know yet exactly how much gain is contributed by the zero. What I can estimate is, if I look at this intersection here, so there's actually the point where there's a tangent placed, this is around, let's say 30, maybe a little bit less, something like this. And from the 8 to 30, maybe 14, I don't know, I will have a gain, additional gain due to the zero of 5, maybe 6 dB. So, of course, this is in total 14, from this red line to this 21, 22, maybe 13. And I will have an additional gain due to the zero of 6 dB or maybe 5 dB. So if I subtract the 14, I do the analysis, 14 dB is the total gain peaking, minus this 6 dB due to the zero, I will have an 8 dB actually due to this gain peaking due to the pair of complex poles. So I can say, due to the pair of complex poles, I have actually a gain peaking of only 8 dB. Maybe it is 9, maybe it is 7, but that doesn't matter at the moment. We are, of course, trying to estimate this as accurate as possible. So let's move on to using these elements. We have now the DC gain, we have now determined the location, estimated actually the location of our zero, and have now an estimate for our gain peaking and also our frequency. So the frequency of the peaking, we haven't discussed this. So this is now the gain peaking, and if I go down vertically at the frequency plot, I can see that there is 1 here, 2, 3, 4, 5, 6, and it happens at 7. So, excuse me, 1, 2, 3, 4, 5, 6. So I will make it 6 radians per second. So I miscounted this one. So it is 1 again, 2, 3, 4, 5, 6. So I have a gain peaking at 6 radians per second, and a gain peaking is, due to the pair of complex poles alone, is estimated as 8 dB, because we have now subtracted the part of the zero. So let's move on by using this elements of this plot and calculate and estimate the transfer function for this system. So that's our next step. Okay, now we have again our Bode plot here with the elements we have discussed shortly. We have the tangent lines and we have the zero and or the gain peaking frequency and also the gain peaking of 8 dBs as discussed shortly. I will use the elements here to determine the transfer function, and I also use this plot as, again, we have discussed in the last video. We will try to use this plot to estimate our damping ratio for our situation here. So if I now look at the situation, let's first begin at DC. So what we have is at omega 0 radians per second, which is DC, I have a gain is 8 dB approximately. And the phase here is, as you can see, is 0 degrees. So this will actually give me a positive gain because there is no sign inversion. And I have now, in scalar form, I have a gain of kdc, will be, of course, as a scalar 10 to the power 8 divided by 20, again at familiar formula, and this will give you approximately 2.5 2.51, but let's use this 2.5. So again, I have now the first dot. The second is the 0. So what is the location of the 0? If I look at this plot here, this 0 was placed at 1, between 1 and 2. So I estimated that at 1.5. So I can say the 0, let me use another color. So I can say the 0, so omega z, we have estimated at 1.5 radians per second. That is our 0 frequency, and we will use that in our transfer function. Now, if I now move on and try to look at the quadratic term, so the gain peaking. So there is a gain peaking in total of course, from 8 to approximately 21, 22, so it is 14 dB, but I subtract the contribution of the 0. So if I now say gain peaking is 22 dB minus 8 dB, because that part, if I make a drawing here, try to make a horizontal line for that part, that is approximately 22, maybe 21, so 22. That is our maximum gain, but it is of course now 14 dB in total. But I've already discussed earlier that the gain contribution by the 0 is also present there. So I have now estimated at this point here from this tangent line, red line, has a length of 6 dB approximately. So actual gain peaking, so the actual gain peaking, so actual peaking will be 14 dB minus the 6 dB due to the 0 only. So that will give us 8 dB of peaking. And I will again place the location of the 0 here. So this is my omega 0, and this is our omega n, our natural frequency. So we will move on with that shortly. So if I now say what is now the omega n here, so omega n is 6 radians per second. You can see it also from the plot. Omega z is 1.5 radians per second. What is determined that? Now, we will now use this plot to estimate or determine actually our zeta, the damping ratio, for having a gain peaking of 8 dB. So if I look at the graph, I see that this is 10 dB, so that's for 0.15. If I go down at the 0.20, it is maybe a little bit larger. I estimated between the 0.20 and 0.25. So I think the 0.25 is a little bit closer to the gain peaking of 8. As you can see, the gain peaking, actually the peak of this blue line is not at that 1. So it is not exactly at that normalized frequency. So that is also an issue. So omega n is not necessarily the resonant frequency. That is a different frequency. But for very low values of zeta, it is almost equal to the resonant frequency. But that is a discussion which is not a part of this video. So I will just use this peak value here. I will just use this. As you can see, that is for 0.25 zeta. I will use that. So I can say for gain peaking, so for gain peaking of 8 dB, the damping ratio from the graph is almost 0.25. Is it exactly 0.25? I don't know. I just estimated. Of course, there's a formula for that, but with the plot, we can move much faster. So let's now continue with our quadratic term, because this will, of course, give us the quadratic term, which is in general form 1 plus 2 zeta times s divided by omega n plus s divided by omega n and the quantity square. So let me also place this in the parentheses. For the 0, I forgot this to mention here. That is of course a situation, or our term is s divided by omega z plus 1. This is actually the term we will use. And the KDC we will also use in our transfer function. Now we have actually the necessary elements, so we can now set up our transfer function. So let's write down the transfer function here. So transfer Okay, I will move with the black color. Okay, what we have is the GS, which is KDC times the product of the zeros in this form, S divided by the omega Z plus 1. And we have only one zero, so that is actually done for the numerator. And we have only the gain peaking and no additional poles or others. So we have just 1 plus 2 zeta times S divided by omega n, and then plus S divided by omega n and the quantity squared. Now I will now substitute the values I have now found from this analysis and also using this plot for our gain peaking. So what is now the value of the KDC, what is now the value of the omega z, and what is the value of zeta and omega n? So let's substitute that here. We have now 2.5 times, and then we make here S divided by 1.5 plus 1, that's just for the zero numerator, and you will now have 1 plus 2 times 0.25, and then times S divided by 6, and then plus S divided by 6 and then quantity squared. Okay, that's actually for our transfer function. Of course, this is not really handy written, so we will now simplify this. First, what I do is I notice here that this is a square, so it will be squared, S squared, and the 6 squared, so that will means 36. So I will now first get rid of this fraction 36. So that's actually our first step. So what I do is I will multiply the numerator and the denominator by 36. Of course, this is just 0.5, so you can already write it down. So what you have is now, and I will use that 36 not in here, but just multiply the this factor 2.5 with it. So what I have is, I will make this clear here, 36 times 22.5 times, and I will leave the 0 here as it is, and divided by, this is now 36, plus, because 1 times 36, and this is 0.25, this is 0.5, and 0.5 times 36 divided by 6 is actually just times 6. So you will actually have here the value of 3. So you will have 3s, and you will have s squared because you are already multiplied by 36. Okay. The next step is, as you can see here, we would like to, of course, have this 1.5 also gone, because I would like to isolate the s. This value we can also calculate. It is just 36 times 2.5. It is actually 90, so we can already write it down. So let's write it down. 90 times s divided by 1.5 plus 1 for our 0 term, and then divided by 36 plus 3s plus s squared. Now, if I now multiply the denominator and the numerator by 1.5, I will of course have here s plus 1.5, which I preferred. But I don't like to change this expression because it was already in the form I want, because I don't want a coefficient here except 1. This can be of course multiplied, but I don't want to screw this expression. So what I want is, I will just take this in parentheses and multiply it by 1.5, and then use this 90 divided by the 1.5 to have that effective parameter for this transfer function. So let's move on with this expression. What we have is then GS is equal to 90 times the s plus 1.5, because I have now multiplied by 1.5. That's for the numerator. And I do now 1.5 times, in parentheses, that term, so which is 36 plus 3s plus s squared. Now, I can simplify this further by having a 90 divided by 1.5, but that's just the coefficient of this transfer function. I leave this the numerator as it is, and I will set this also from the higher order to the lower order. So that is what is done usually. So I will do that. In the next step, for my transfer function, what I have is that 90 divided by 1.5, so it is 60 in effect, times s plus 1.5 divided by s squared plus 3s plus 36. And now this is our final result of our transfer function, what we are looking for. As you can see, we have a 0 at 1.5 and we have a expression for the pair of complex poles as shown here. If you plot this and compare it to the actual Bode plot, which is given now in this example, that can have some differences. That is really normal. You might have that your peaking is a little bit larger or a little bit smaller, but you can already check something actually in this transfer function. For example, if you look at the DC gain, if you set the S is equal to 0, which is the condition for DC, or omega is equal to 0, you will have 60 times 1.5 divided by 36, and that is 2.5. And if you of course have 2.5 converted to the dBs, you will get very close to 8 dB. And that's actually what we had here also. So that is already correct, but it can be that not all points are equivalent to this expression. So what you then can do after this expression, you can fine-tune your transfer function by looking at the actual transfer function, actual Bode given here. So if you have a larger gain peaking or smaller gain peaking, you might ask, how can I adjust this transfer function by adjusting that gain peaking? So your gain peaking will of course increase by decreasing your damping ratio. So if you increase your damping ratio, you will reduce your gain peaking. If you reduce your or lower your gain damping ratio, you will increase your gain peaking. So there is also a relationship here given. Okay, that is for this example. I hope this clarifies the situation even more with this second example about the Bode plot with gain peaking. If you have questions, comments or suggestions, please let me know in the comment section and we will try to answer them as soon as possible. Thank you very much and see you next time and take care.